CLI and a cross-platform IDE for C and C++. Download now.
Six impossible things. Always a challenge when you choose a number in a talk. If you tell people you're going to do the top 10 something, the top 5 something, or 97 things, you're kind of committed. And we all know that hard coding numbers into our code like that is not a good idea, but it is certainly memorable. My name is Kevlin Henney. You can find me in a number of places online. Somewhat internet unique name, so I'm fairly easy to find. Feel free to connect with me on LinkedIn or follow me on Blue Sky or Mastodon. And so Phil mentioned, I'm taking this quote from Alice Munro, to be precise, the second book, Through the Looking Glass, and what Alice found there. And this is illustration by John Tenniel for the original books, the original Alice books by Lewis Carroll. And the whole thing here is that Alice tells the White Queen that something is impossible, and the White Queen is not impressed by this. Alice says, "There's no use trying. One can't believe impossible things." And the White Queen responds, "Sometimes I've believed as many as 6 impossible things before breakfast." Now, the whole point is, we're in software development. We actually believe impossible things all the time. But I would say actually most of the things we believe are impossible are not impossible. They're just very, very hard. I've done this on social media where I've asked people for the ideas that have gone into this talk. This talk was born, the original version of this talk was born during the pandemic. I also toyed with the idea of doing some other follow-ups and explorations and asked people for impossible things. And most of the things that people described were just very hard, things that might not be achievable by humanity in the next million years. So what I mean by impossible is impossible, not possible, but not likely within the next million years is not impossible. It's just the probability of it happening, the possibility of it happening is so close to 0 that it's probably a floating point rounding to 0. But we're not talking about floating point numbers. We're talking about real stuff. I'm talking about things that are genuinely impossible. Does this matter to your day-to-day work? Well, yes, it does, because this can mislead us. It can cause us to create errors, introduce bugs. It can, some of the things that people lovingly dub undefined behavior are actually to do with impossibilities. It can misguide us when we are talking about the structure and nature of our project schedules as well. So I'm going to start off, I'm going to do it as a countdown. Number 6, representations can be infinite. Now, this is the thing. You can't have infinite representations. The point is, nothing in nature is truly infinite. Infinity is a mathematical construct. It's created by humans. Okay, the universe is not maths. Physics is what governs the universe, and mathematics is simply our ability to imagine and create formal systems. And some of these happen to describe the universe, which is why mathematics is unreasonably good at doing it, because it defines a lot of things or allows us to describe things that are also unreasonable. So there's no mysticism. Mathematics is not more fundamental than physics. So I'm obviously picking a fight there. Feel free to come to Gathertown and discuss it and learn that you are wrong. Nothing in nature is truly infinite. It's a construct. Even if you go, I live in Bristol. This is one from the Bristol Beer Factory. You can get infinity, but of course it is artificial. It is created by us. Now, the most familiar source of infinity is the stuff that we deal with in floating point numbers. This is not infinity. It is a macro. It can be found in math.h or cmath. It's a way of talking about the thing that cannot be represented, but it is not itself infinite. It has a very specific bitwise representation. If you would like a convenient source of infinity, you can divide 1 by 0. And a lot of people think the 1 divided by 0 is indeed infinity, but actually mathematics on this count is fairly straightforward. Division by 0 is actually undefined for real numbers in the real number system. And this whole notion, why does this trip us up? Well, a number of years ago, I edited this book, 97 Things Every Programmer Should Know. And the genesis of this book was there had already been a 97 Things Every Software Architect Should Know, and I was party to the creation of that, and I also contributed to that. And it was one summer I'd been looking at some code, and I was, mildly frustrated. Somebody had kind of stumbled across a floating point issue, and I remember just saying out loud to myself, "Oh, that's just something that every programmer should know." And I suddenly thought, "Wait a minute, maybe there's a book in this." This is actually the only piece that I specifically asked somebody to write. It was an open call, and I did approach a number of people, but I also got people to just contribute. This is effectively an open source book as well. But it's the only person I contacted, Chuck Allison, who used to be involved very heavily in the core C++ world. And he'd written some really good stuff on floating point numbers. And I said, "Look, Chuck, it'd be really helpful if you could just write a distilled piece of 500 or 600 words." And I even gave him a title, "Floating Point Numbers Aren't Real." And as Chuck observes, real numbers have infinite precision and are therefore continuous and non-lossy. One of the things that sometimes people stumble across when they move into languages with floating point numbers, particularly if they've come from kind of a much older school kind of approach, say COBOL, is they're not really familiar with the idea and weirdness of floating point numbers and indeed their motivation. And they solve a very specific problem. It just happens that currency calculations are not that problem. The whole point is that these numbers are not real. Any language that, like Fortran, that tells you it's got real numbers and uses the name real for its type is lying to you. So I'm quite happy to have names like float and stuff like that, because they are accurate representations rather than over-promising. Floating point numbers have limited precision, so they are finite. And they resemble badly behaved integers. They do not have a consistent spacing, and that sometimes surprises people, leads to all kinds of exciting errors. But badly behaved integers, that also raises another question. How badly behaved are integers? They're actually quite badly behaved. So I'm going to look at this. There's this wonderful observation from Richard Dalton 10 years ago. Fsbuzz was invented to avoid the awkwardness of realizing nobody in the room can binary search an array. Now, in your head, you're either going like, yeah, I think I can do that, or, oh, I think I remember how to do that. But it's worth pointing out that even when you think you know, you're probably slightly wrong. So I dug this out of an old C++ book. It was published in the 1990s. As you can tell, it's a binary search. And so I'm going to reformat it because I don't believe that we're on a space budget, and yeah, spacing, it often helps. And I do also believe that we're using C++, so there's a few other bits and pieces. So okay, I've tidied it up, and there's a few other idiomatic aspects that I might wish to address, and I certainly would have done back in the 90s as well. This is not merely an artifact of the 1990s. No, I wouldn't write it like this even back then. But if you look closely, you can see there is actually a kind of a three-way partitioning going on here. And this is the idea is that we are being this binary search is, it's not simply returning where a thing is, it's returning where it would be if it were there. So if you are looking for something and it's not there, it'll locate where it would be if you were to add it. And that's an interesting one. This is a feature that is shared with this algorithm. And this algorithm is pseudocoded and was originally written by John Bentley. And it was done back in 83. And there's a kind of an interesting thing about this. This was used extensively, this three-way partitioning, and where would it be? It found its way into a lot of different algorithm implementations. Now, what is interesting here is that this was part of his communications of the ACM column, Programming Pearls, which some of you may be aware he collected some of these into books, which are actually they still have a lot to teach us, even though they're quite old at this point. And it was a piece on writing correct programs. He was advocating formal proofs, and so marked up and annotated with invariants, the code looks a bit like this. Now, and this is wonderful. And he goes through and he talks about program verification, and he verifies that this algorithm works. And he says one of the major benefits of program verification is that it gives programs a language in which they can express that understanding that they have of how things work, rather than just going by an intuition. Let's actually put that understanding out into the world and reason about it using a formal system. Okay, fantastic. So we have some kind of rigor there and some kind of assurance of that. But he also acknowledges this is not the whole story. And as we know, formal methods did not really pan out in the way that many people in the 80s expected them to. These techniques are only a small part of writing correct programs. Keeping the code simple is usually the key to correctness. Yes, absolutely. But he also points something else out, which I think is really important. Ironically so, in fact. On the other hand, several professional programmers familiar with these techniques have related to me an experience that is too common in my own programming. When they construct a program, the hard parts work the first time, while the bugs are in the easy parts. You know this, you've done this, where sometimes you know there's a hard change that you've got to do, and you are busy. You are keeping all the plates in the air, and you're going like, okay, here's the really difficult bit, here's the really difficult bit, and you adjust it, you make your mods, you do whatever, fantastic. You totally trip up over something else that you forgot to also update, or an initialization that needed to be changed as a result of everything you were doing. You often trip up over the easy parts and get the hard part right when you're really focused on that. And that's the point. Focus is a finite human resource. You cannot focus on everything because then you're not focused by definition. It's built into the definition of attention and focus. So you take your eye off something that seems trivial, and yeah, that's your off by ones, that's your incorrect initializations, bits of erroneous behavior, and so on. But why does this matter here? Well, this matters because here's a piece of Java code. This piece of Java code was in the main Java library from the late 90s to 2006. It's a binary search, and it follows exactly the Bentley algorithm, which is not surprising. It was developed by Josh Block, who was a student of Bentley. And you know, this all works absolutely fine. The problem is it doesn't work for very large arrays. This is incorrect. There is a point here. When you add a very large integer to another very large integer, what happens? Well, in Java, it's guaranteed to wrap around and become very negative, and you divide that by 2, you don't get what you were expecting. In C++, the standard doesn't guarantee it, but guess what? It wraps around. You know, unless you have a specific need, or you know, it's a very edge case that there are systems that will actually trap this. It's strictly speaking, yeah, this is not defined behavior at this point. In practice, this is the difference between theory and practice. People rely on that, and indeed, pretty much every system that Java was written in C, it relies on that. Of course, it does. It wraps around. It just doesn't work because integers are unbounded. They are infinite. It turns out that computing machines are not. So yeah, this works, and it worked in the 1980s because we couldn't actually get 32-bit addressing or fill up 32-bit addressing. If you've got 32-bit ins, that implies that you are going to have basically 2 billion addressable elements in your array. There was 2 billion of nothing when it came to computers in the 1980s. So yeah, this survived up until the mid-2000s, where we hit a point of inflection in terms of memory. And guess what? This is a bug. So you fix that by recognizing that it turns out that these two statements that are mathematically equivalent are not computationally equivalent. So we fix that. The problem here is it goes back to the original proof. He proved perfectly that for perfect integers, this will work. This is his assumption, which of course is that tragic irony of a piece of writing called Writing Correct Programs. There was a bug in it, and it sat there for a couple of decades. So is this a complete surprise? Well, no, we knew about this. It's just a blind spot. It's that attention thing. It's to do with assumptions. If I take you back to 1972, so over 10 years before that was written, Dijkstra observes, in one particular demonstration of something, he says, I have assumed perfect arithmetic. In my experience, the validity of such proofs often gets questioned by people who argue that in practice, one never has perfect arithmetic at one's disposal. Admissible integer values usually have an absolute upper bound. Real numbers are only represented to a finite accuracy, etc. So what is the validity of such proofs? Well, if one proves the correctness of a program assuming an idealized perfect world, one should not be amazed if something goes wrong when this ideal program gets executed by an imperfect implementation. And yeah, there we have it. And if we go back to that bin search that I showed you earlier on, there's the offending line, exactly the same issue. Now, okay, let's fast forward. We're in the 21st century. We've got C++, which has a far richer library than was available. You would address this issue, and this is a known issue. You don't really need to kind of worry about what expression you're going to use if the expression looks like this. You want the midpoint. That's what you want. You don't want to add two things and divide by two. You don't want to subtract the difference and divide by two and know all the rest of it. You want to find the midpoint. Let's actually program by intention. And at this point, we've got a function in the library, that actually allows us to describe that intention. Now, of course, there's no point in doing this because we already have that behavior. If we're actually looking for, where is it? And if it isn't there, where is it? We've already got it. It's in the library. And if we're doing that, we can just get rid of the wrapper function and we're done. By the way, this is also a lesson in what to do with legacy code. I don't care if somebody says it works. If the center of gravity, over time, the center of gravity of what is commodified by a platform, everything from the hardware through the operating system up through your libraries, there's a kind of a general lowering of the center of gravity. This was an observation that was made by the late Hubert Matthews many years ago. And this idea is that some of the things that you had to work for are now just available off the shelf. Use them. Don't give somebody that maintenance burden. I don't care if they say it works. We've just demonstrated this piece of code did not work. It is not your problem to solve the midpoint problem. You're probably doing something else. So, as libraries progress, it is in your interest to migrate to them. Now, that's the first one. Representations can be infinite. No, they can't. We know that, and there is nothing you can do about it. The universe is not going to accommodate that. It is also not going to accommodate this, the idea that every question has an answer. To be precise, every question has an answer within the frame in which you asked it. And that has a number of interesting consequences, both in terms of error modes as well as computability. One of my favorite examples of this is actually from about 10 years ago. This is Facebook. And so one day, I can't remember what the issue was. I'm pretty sure it wasn't fixed. But I decided I would clearly, I was either very annoyed or I had an abundance of time on my hand. And this is back before Facebook was destroying democracy. I just thought, I'll give them some feedback because rather than moan about the bug, I feel, morally obliged to report it. And so I received this message. Your feedback will be used to improve Facebook. No. Thanks for taking the time to make a report. As you can see, time is the issue here. 31st of December, 1969. That predates an awful lot of things, including Facebook. And so, for a number of you, you're looking at that going, oh, wait a minute, I don't know about 1969, but I can tell you about 1970. Yeah, this is kind of suspicious. The time, let's go and look at this. This is the POSIX standard. The time function, which is defined in the C standard, but the definition in the C standard is pretty loosey-goosey. POSIX nails it down to pretty much what every system is going to do, but systems are entitled to be different. Of course, we recognize that. But honestly, if you're working on a system that doesn't use the same epoch time, as we all know, which is, well, we're going to find out, the beginning of time, it's not really, forget it. The C standard is a bit wet on this one. Let's be serious. The problem here is, what if that value is 0? What if we end up with the value 0? 0 is a very common thing to end up with. And indeed, it turns out all you need to do is look around and you will find the beginning of time. So here's one that was sent to me last year from the Netherlands, quite an old episode. There we go. Apparently that episode available 1st of January, 1970, midnight. Yeah, probably wasn't available back then. That's the beginning of time. Now, there's a couple of points here. Don't forget there's the end of time as well, the Unix apocalypse, 2038. It'll be in January. If you are in a time zone somewhere around Europe, it'll be morning. If it all goes horribly wrong, it's fine. You'll be asleep. It's going to be just before 3:15 in the morning GMT. End of the world. You'll be asleep. So convenient. So, I'm kind of hoping to live after that. And given that I was born before this, that kind of makes me an eternal. I was born before the beginning of time and hope to live beyond the end of time. Again, the finiteness of integers. This comes about. Okay, so that's a limitation of signed 32-bit integers. Now, my thinking originally on this was, hey, we've got 0 there. That gets us to midnight 1970. And then, wait a minute, I'm in the UK, which is significantly further east than, say, where Facebook servers are. And so Facebook, well, basically, I would have to go west, which is negative. So if I go negative from midnight, that takes me into the 31st of December, 1969. That was my original thinking. Now, guess what? It also turns out, Anil Dash is exactly right. The natural enemy of the programmer is the time zone. I have noticed a number of bugs. This bug can be found. This bug can be found in the National Rail software for the UK, and I think it's also you can find it on Eurostar. This is a trip that I took last summer, and this is my return. I returned from Rotterdam to London, and as you can see, the time in Rotterdam was just before 9 o'clock, and I will be arriving back in London just before midday. And you might say, well, those are 3 hours apart. Except for those of you who know anything about geography, will go, wait a minute, aren't these guys 1 hour apart? Shouldn't that be a 4-hour? Shouldn't that be a 4-hour journey, not a 2 hour 59 journey as reported? Shouldn't it be 3 hours 59, especially with one change? Yeah, and this has been this bug. There's been a bug that has been present in some of the reporting systems for Eurostar since Eurostar was originally started running in the 1990s. So not only do we have some of these bugs, but some of these bugs are in one sense timeless. They are with us for the whole journey. So that was one theory. But actually, there is a more likely theory that I have also that I realized sometime later. You don't need to go hours back into 1969. You don't need to go from the beginning of time back a few hours. You could go just 1 second, and that gets you to the 31st of December, -1. So what, instead of a convenient source of 0, which is probably an uninitialized variable, okay, and before anybody jumps on and says, oh, but that's undefined behavior. There's no such thing as undefined behavior. Undefined behavior is an artifact of a specification. When something runs in the real world, you get behavior. It doesn't mean that magic happens. You get something. And in a number of cases, these undefined or soon to be erroneous values are actually really well defined as 0 just because of the way that things work out. So, 0 convenient, but where do I get -1 from? Where I need a convenient source of -1. That's not obvious until, let's dig into the C library. Yeah, guess what? If you call the time function and time is not available, you get -1. And this is important because people often think, oh, I can just call time. Wherever I am, time is available. That's actually not true. Time is time. I'm going to quote from Interstellar and the character of Amelia Brand. We need to think of time as a resource. It's not just available everywhere. You can't just call. In fact, everybody does this. It doesn't matter what language you're in. People often think, oh, I'll just call the current time and get the time, and that's it. And they've had that plastered through their code. You need to think of it like a resource. How do you deal with resources? Okay, your resources are fallible. Resources are passed around. You don't just globally access. Well, maybe you do, but that's that's a job for life then, and we call that legacy code. You pass a resource around. Here is the file that I have opened for you. Here is the network connection. Here is the source of time. Okay, time is fallible, and we know that from the real world. There's not a unique source of time. Sitting in my office right here, I can currently see 4 sources of time. Okay, I've got an analog clock right in front of me. I've got an analog watch to my left. I'm not even sure that's on the right time zone. I never look at it. I've got a digital readout right in front of me and to my right. According to this, my office is approximately 1 light minute across. Okay, they all tell different times. In fact, the other day, the analog clock, the battery ran out. In other words, time failed. Time is a resource. It does sometimes fail. So that's a convenient source of the -1, which takes you 1 second back into 1969. Now, this is a point. What we've done here, when we've asked the question, what is the time? We have had -1 return. The problem is that -1 is also a valid time. We've ended up using the same range to express the failure value as the success value. And you can see that that's going to be a little problematic. And you might think, oh, Kevin, it's just to do with error reporting. Well, yeah, and kind of, but we weren't able to answer the question on the terms in which it was asked. If somebody asks you a yes/no question and it doesn't even make sense to answer yes or no, but you're only given the bandwidth to answer yes or no, you're stuck. And it doesn't matter if you've got 4 billion yes or no's, you know, in this particular case, you're still stuck in terms of how you deal with that. And you have to recognize that. Now, we might say, well, let's choose a sentinel value to represent that. Okay, well, we can do that. Let's have an exploration. Again, let's get mathematical here. Let's have an exploration and see some of these things. I'm going to write a function for the arithmetic mean, okay, an average function, and it's fairly average in its implementation. I'm going to accumulate. I'm just simply going to add up. I've been given something. I'm presuming it's an array of numbers or a range of numbers of some kind. I'm going to use just old-style iterators for this. Initialize that with 0.0. We're just going to assume that we are dealing with floating point numbers. And then I am going to divide that by the distance there. Okay, and that gives us the mean. Okay, that's great. So let's take an example. Let's make this concrete. I've got some values there. I'm going to initialize those. That's just going to be an initializer list, and that's fine for our purposes. We're going to look at the beginning and the ending, and we're going to look at that, and that's great. Great. Given this, when we take the arithmetic mean from the beginning to the ending, then what do we get? I'll leave you a moment to kind of figure that one out. And by the way, you don't have to worry about floating point approximations. This one does. The numbers were carefully chosen. Hey, 3.5. Fantastic. Great. Okay, that's good. Now, some of you might have been thinking, yeah, but Kevlin, what if I pass an empty range? What if we end where we begin? There are no values. That implementation, the distance is 0. What is going to be the effective, it's going to be 0 divided by 0. And what's that? Well, I showed you what 1 divided by 0 was earlier on. And I showed you that because it's got nothing to do with the answer here. It's nan. 0.0 divided by 0.0 is well defined to be nan. It's in the IEEE 754 standard. You are guaranteed that on an IEEE 754 implementation for floating point. So division by 0 does not give you infinity necessarily. If you are dividing 0 by 0, you are well defined to do this. Occasionally people will point to this as being a JavaScript issue, because we all encountered that on websites, but no, it's not a JavaScript thing. This dates back to the 1980s. This is what we're guaranteed, okay? That gives you that. Nan is a way of saying, hey, guess what? There is no answer in the frame in which you asked it. You asked for a number. You asked for a floating point number, and I'm sorry I can't answer that question because the result is not a number. As I said, we get a lot of JavaScript stuff with this. So, and I love the self-reference here from a bug I got a few years ago from Lufthansa. Trying to parse nan, but it is not a number. How truthful is that? But nan as a way of saying, I'm sorry, we have no response to you, it still ends up being used in the context of a floating point number. Now, sometimes people will look at this and maybe you looked at it a bit further back, say, oh, these things should return, they should return optional or something equivalent to that. It's like, yeah, up to a point. There are distinct reasons why that's not the case, because optional is not an IEEE 754 thing, and there is a cost associated with that with respect to raw floating point. And floating point is incredibly portable. Not totally, but there are some issues, but it is surprisingly portable. If you're old enough to have programmed on non-IEEE 754, you will totally understand what I'm saying here. But the problem is because we have tried to respond within the frame, we've said, oh, it's a double. We've got a problem here because it doesn't play nicely. It doesn't compose. So let's try a set. Let's just take a set of doubles. Okay, we've got values. I'm going to insert 0. I'm going to insert 42. I'm going to insert minus 273.15. Okay, the size of this is 3. There are no surprises here. Now I'm going to insert nan. Now I want you to think about this one for a moment. What's the size going to be? I'm going to insert nan. It's 3. Nan doesn't get inserted. Let's try putting nan in first. What's the size here? 1. Once it's in there, it poisons the whole collection. You can't put anything else in. In fact, we can even try and count, and there we go. There's 1 in there. Yeah, this is kind of a false positive. If we put that there, which we said does not include nan, it still counts 1. In fact, if we don't insert nan at all, we always get a count of 1. In fact, if you make it a multi-set, you discover there are 3 in there, a multi-set with 3 items. Right, in other words, count does not terminate. Count uses the less than, the point is nan does not compare equal to anything, but more importantly, equality is not used for these comparisons in the ordered associative containers. Like set and multi-set and map and multi-map. It's not, less than is used. And so therefore things are ordered with respect to less than and greater than. And it turns out that nothing is less than and nothing is greater than. So there, this is also that kind of reminder that not equals is not the same as not less than, if something is greater than or less than. In some languages, you may have learned this is the symbol for not equals. The problem is these two concepts are not actually equivalent. So yeah, nan surprises people in calculations and everywhere. Early on in the pandemic, we had a driverless racing car crash into a wall because a nan was generated. In the initialization lab, something caused the steering control signal to go to nan, and the steering locked to the maximum value to the right. So for those of you who are wondering about self-driving cars, yeah, this is the kind of code we've got to deal with. And no, this wasn't JavaScript and it wasn't C++. I believe it was MATLAB code. This idea obviously leaks into the world. This is a picture I took many, many years ago, back when phones first started getting cameras. I found that there was this, and this is Paddington Station in London, which heads west. So Aachen is actually in the wrong direction. And no, there are no direct routes from Aachen. This is test data. Now, this whole idea is actually much, much deeper. The whole idea here is it's not simply a case of, it's not simply what I'm saying here when I say that every question has an answer. I'm actually, that it's not just that every question doesn't have an answer, and it's not just about the representation in terms of the return value. That please don't mistake it for that. Let's just kind of go back to this. I don't know, have you ever experienced this? I experience this all the time. You go onto an app, you go onto a website. And maybe it's a shopping cart thing. Maybe it's, here's a list of your stuff. Here's your money or whatever it is. And initially it says, hey, you have nothing. Your heart jumps for a moment. And then a moment later, boom, there's your stuff. What? How did I have nothing and then something? What is going on here? This is ridiculous. John Carmack of id fame and Doom, Wolfenstein, and all the rest of it, made the observation a number of years ago, a large fraction of the flaws in software development are due to programmers not fully understanding all the possible states their code may execute in. What's going on here is that people have assumed the thing that we can't have, which is infinite speed. They have assumed that everything has infinite speed, therefore things take 0 time. We will be talking about networking and distribution a little bit later. But there is latency. The real world has latency. And so therefore, they've implemented this. By default, the container size is 0 at the beginning, and they've made it displayable. And then they get a loaded, here's the data, and suddenly this gets updated. The correct state model for this is we are loading, we don't display because the size is 0, but we are in a state that is not yet ready. We have a not available state. Then when we're loaded, we have the data available. So in other words, this is a signal to write stuff like this. Now, I'm sure you've come across this quote. It's kind of a classic one from Phil Carlton. There are only 2 hard things in computer science: cache and validation, and naming things. I want to focus on naming things here, because a lot of the issues when we talk about every question has an answer are to do with our understanding of algorithms. Now, one of the things that I find fascinating is that we have this header in C++, and it's called algorithm. The one thing it pretty much doesn't contain is algorithms. And people will quite confidently in conversation say, oh, yes, use the sort algorithm. Oh, you need to... Algorithm maybe makes you sound cool. The problem is, if you know what an algorithm is, you know that that's not what's in this header. This rather wonderful book on the kind of history of almost the history of impossibility, but late 19th and early 20th century mathematics, and Gödel, and well, it's partly a biography of Russell, but obviously it deals with Gödel and Gödel's incompleteness theorems. They have a definition of algorithm: a methodical step-by-step procedure described in terms of totally unambiguous instructions, which starts at a specified initial condition and eventually terminates with the desired outcome. That's great. So we've got std find. What is that? Well, actually, if you were naming it as an algorithm, it would be linear search. That one, actually, pretty much there is no other way to do it. I mean, we do name things after these. I mean, the slightly not useful binary search, why we end up using lower range. But my favorite example is sort, because sort is not an algorithm. Sort is a state. It's a description of an output state. It is not an algorithm. I haven't told you how to get there. Most standard library implementations use interest sort. That's an algorithm. Sort is not an algorithm. Yeah. So your implementations will contain algorithms that conform to expectations, but those expectations, in most cases, and for find, as I say, yeah, there is kind of, it's a linear search. We can tell that. Binary search is binary search. Lower range is actually a binary search, but sort is not guaranteed or required to be interest sort. But sort on its own is not an algorithm. That's why books on sorting or books on algorithms have a whole chapter of it. Because if it were, they were just the sort algorithm, it'd be done. So let's have a look at something something a little bit crazy. Let's try. This is a not safe for work algorithm, permutation sort. It's got factorial complexity. OMG. In essence, it's an unoptimized search through the permutations of input values until it finds the one arrangement that is sorted. Really simple implementation in C++. We just go through all the permutations until we hit one that's sorted. Fantastic. This is terrible, terrible, terrible performance. You know, in the worst case, if you've got 10 items, you will be doing 3 million comparisons. Surely there can be nothing worse than this. Yeah, hold my beer. Hold my beer. Don't be so sure. There's BOGO sort, which does this randomly. So we can write this like this. This is often how people will write it. I generally don't advocate this approach. Because in the situation that this is actually sorted, then it will terminate quickly. We don't want that. We want that. We want the joy and delight of uncertainty. Make sure you shuffle it before you do any checking. Now, the next thing is random shuffle has been deprecated somewhat annoyingly, and people give me all kinds of arbitrary reasons for it. C++ makes using random numbers really hard. There are three cases for using there are three distinct uses for random numbers. One of them is where we want to have sequences that are statistically, qualitatively like random numbers, but they are repeatable. So running large simulations. For cryptography, we would like things not to be pseudo-random. We prefer them to be actually random because we don't want somebody to be able to repeat the sequence. That's great. C++ accommodates these two audiences very clearly. And then there's a third people who just want a third group, the people who just want to mix it up. Random shuffle does that for you. And now it's been deprecated. I'm going to say that was a really bad idea. And the reasons for deprecation were also quite weak. They were based on common implementations rather than telling people to fix their implementations. We are used to people fixing their implementations all the time. That's why you get security patches. So that was a bit of a wrong move, but we acknowledge this. We're going to I'm going to get involved in the Mersenne twister here. Teaching random numbers to C++ developers is a pain in the backside when every other language allows you to do it straight out. Yeah, that third group is the largest group of users of random numbers. If you have three audiences, you need to accommodate them carefully. Now, of course, there is this observation from John von Neumann. Anyone who considers arithmetical methods of producing random numbers is, of course, in a state of sin. Okay, let's be less sinful and use true randomness, which we can get from the entropy of our device. Normally, we don't use it directly. We will use it to seed. And there we have a very fine implementation of BOGO sort. But we have a question. Is it? Is it an algorithm? Well, no, it isn't, because a procedure which always terminates is called an algorithm. We're not guaranteed that's ever going to terminate. Yeah, there's actually a simple proof by induction that I've got on a blog post on this that demonstrates you're not guaranteed that BOGO sort will ever terminate. Now, of course, statistically, every time I've ever run it, it has terminated. Think about that statement for a moment. We'll come back to that. So let's go back to this. We need to test this. Program testing can be used to show the presence of bugs but never show their absence. Let's have a look at this. I've got some values here. I'm going to BOGO sort this range. I'm going to assert that it's sorted. I guess I ought to also, it's not enough that it's sorted. I actually need to assert that it's the original values. I can do this via this complex approach of checking the permutations, and alternatively, I can just tell you what I was expecting and then assert against that. Yeah, this is going to be much better. However, what we need is that this must terminate before infinity. So why don't we set a signal that will execute at infinity and fail the test if we reach infinity? And how are we going to delay this? Well, we're going to set the alarm for infinity. So if it hasn't terminated by infinity, then this alarm will be triggered and we will fail the test. You can see there's a couple of problems here, not least of which is alarm expects an unsigned. Don't forget to cancel the alarm. We can cast that. Now, of course, in practicality, we're not going to do that. And honestly, every time I ever run it, I've never had the situation where I've had to hit Control-C. I only use small examples, but it does demonstrate how we fix the halting problem, or rather how we address that. We trade the fact that something might never terminate for certainty in time, uncertainty of result, which leads us nicely into this other challenge that we have. Here's another impossibility. Every truth can be established where it applies. And this applies to things like the halting problem, like Gödel's incompleteness theorems, which is basically, this all kind of went to hell back in the earlier part of the last century. As Adrian Collier observes, Bertrand Russell and Alfred North Whitehead, also the subject of that book, Logicomics, published Principia Mathematica, which is profoundly unreadable and takes about 300 pages to demonstrate that 1 + 1 is 2, with the goal of providing solid foundations for all mathematics. They wanted to demonstrate mathematics was complete and consistent. And this looked like it might work out, and then that bubble was burst. Gödel's incompleteness theorem, well, actually, two theorems, incompleteness theorems, shattered the dream, showing that for any consistent axiomatic system, there will always be theorems that cannot be proven within that system. Put another way, when you are within a formal space, and they're using natural numbers, but we use code. When you're within a formal space, there are certain things within that that you cannot demonstrate are true within that system. To demonstrate their truth, you have to step outside that system. This is also the subject of a rather classic book, Gödel, Escher, Bach. As they said, all consistent axiomatic formulations in number theory include undecidable propositions. They cannot be decided. There are certain things that cannot be known. Now, languages like C and C++, yeah, there's a kind of a move towards safety, but I mean, that's kind of way out there on the horizon. You know, it's in the distance. The moves are there, which means that it's really easy to find an example of undecidability. How long is a piece of string? Okay, I'm going to do this in C because that keeps things nice and easy. Ready, more sources of, ready source of undefined behavior, similar number of sources as say C++ has, but less fewer guardrails. So, generally we don't recommend that people in C are using this, but in C you have no choice. So we're going to find the length of a string being defined as a null terminated sequence of characters. Okay, so that's great. And so what I've got is I start off with 0, I loop until I find the null terminator, I simply increment each time round and I return the number of times I did that, and there it is, the length. What must be true for this to work? Well, first thing is the pointer that you're being passed can't be null. Okay, actually, this is a really easy case to deal with. This is not an interesting one. This is the one that's interesting. And it's particularly interesting. It's in gray here. It's very interesting. Why is it particularly interesting? It's particularly interesting because you can't actually write it in C. This is basically a precondition on this. What it says is that we need there to exist a null that is reachable through valid chars. You can, inside the system of standards, inside the system of Strlen, which is inside the system of standard C, there is no way I can demonstrate the truth of this statement. If I put this outside, I can demonstrate by construction that something is correct. I can easily look at something and go like, hey, this is not actually valid. But what we're doing here is we are basically saying that there exists a null terminator across defined memory space. You can't do that. That's not a provable thing inside the system of Strlen. And we, as I said, from outside, we can do it simply by inspection. Here we can see that this is well defined, be excellent to each other. There's char, we're going to do a print f, and it's just like, yeah, prints out, be excellent to each other. The length of that string is 26. But what if I have insufficient space? What if I only give 5 characters and I don't give space for a null? In fact, C allows us to initialize it in a way that is slightly deceptive. We normally read there being an implied null on the end. There isn't in this particular case. This is not defined behavior. In C++, it'll become erroneous behavior, but the point here is that this may actually return the right result, because memory is not normally doled out in 5-byte chunks. There's normally going to be 6 or 8 bytes, and there's a fairly good chance that extra memory will be nulled, and you may get this. Coincidentally, it'll turn out to be right, but this is technically undefined behavior, so you may find yourself touching the void. An uninitialized pointer, very easy to diagnose, but wow, is this a biggie? This one gives you far worse garbage than the previous one. And you know, Wittgenstein, in dealing with all of this logic and stuff in the early part of the century, did observe, whereof one cannot speak, thereof one must be silent. We had, you know, this is some bad stuff, readily accessible. Now, that's kind of nice, interesting little bugs. And we might say, well, there's a bunch of things we can do about it. Yeah, you're going to mitigate that. You're never going to get rid of these these issues of incompleteness theorem. They just pop up every now and then. But there are some deeper things, particularly in this era of machine learning. Adrian Collier observes one premise of many models of fairness in machine learning is that you can measure or prove the fairness of a machine learning model from within the system, from properties of the model itself and the data it is trained on. People make that statement. It's a marketing statement as well. The problem is that actually we've known since 1931 that that's not the case. To show that a machine learning model is fair, you need information from outside the system. You cannot rely on your training data. The whole point is you cannot then say it's fair with respect to our training data if we use fairness and our training data as a closed universe. The point is the real world in this sense is not closed from this. And you have to look at something else. There needs to be supplementary information to make the correct judgment. Otherwise, you are inferring and relying heavily on implication. And we can see the kind of perils of this. A wonderful demonstration of this came early on in the pandemic. There's a German artist in Berlin, Simon Beckert, and what you're seeing here is a kind of a cart with 99 secondhand Android phones. And if you remember back to the early days of the pandemic, yeah, we weren't really driving around and going places that much. So this is what Simon Beckert did. Simon Beckert walked around the streets of Berlin causing traffic jams because there was a correlation. Suddenly you've got 99 smartphones, or 99 smartphones moving at walking speed down a road. You might say, wait a minute, that means that there are at least 99 people and of the order of potentially 50 to 200 vehicles moving really slowly. Therefore, that is a traffic jam. There is no therefore in all of this. And this is a real reminder that we've got to be really careful with the stats that are used. And particularly if, we're all experiencing it. Your favorite show gets cancelled after one season. Absolutely, this is not the way to run a business. They're absolute lightweights, some of these executives. They have no concept of the long term. People get really upset, but they don't go back to those series. Whereas I've been recently watching stuff that's 20 years old because I know that it finished. I know it completed. I can watch it all the way to the end because there is an end. Because they're incorrectly measuring in the same way that most web marketing companies and advertising companies and basing their revenue on engagement. The problem is that they're not measuring engagement. The state of, I know what engagement is. It's the state of being engaged. It's emotional involvement or commitment. What they're measuring is engagement. They just need to realize it's in quotes. They're just measuring clicks and shares. And this is important because that's the whole point. We must be careful not to confuse data with the abstractions we use to analyze them. Okay. If you've got data from phones, that doesn't mean there's a traffic jam. Oh, there's a high probability, but it's not one. So this is a really important. You cannot establish the truth of that statement where it is. You need more information. You need to go outside the system of information that you have in order to demonstrate and decide on certain propositions. Now, related to this, but I'm going to separate it out as a very particular perspective. The future is knowable before it happens. Now, that feels like, well, it's obviously impossible. Sure, but why and where do we get tripped up by this? Now, the great Grace Hopper, she observed, to me, programming is more than an important practical art. It is also a gigantic undertaking in the foundations of knowledge. What we do is quite literally codify knowledge when we write code. We are codifying an understanding of the problem domain, married with an understanding of the solution domain, married with our choices based on our knowledge of these. We are saying it is our belief that this is how we do it, and this is how we express this. A code base is a codification of knowledge, but it's contingent. Now, the thing is, there are different ways of ranking knowledge. And there's a scheme Philip Armour came up with quarter of a century back, 5 orders of ignorance. Starts at 0, nice. Lack of ignorance, you know what you know. Lack of knowledge, okay? Sorry, you know what you don't know. You know what you know what you don't know. Lack of awareness, you don't know what you don't know. Lack of process, you don't know how to find out what you don't know. And meta-ignorance, you don't know the 5 orders of ignorance. Well, we do. So let's just reduce it to these 4 and reframe it. The known knowns, the known unknowns, the unknown unknowns, and the unknowable unknowns. And when I say something is an unknowable unknown, what I mean is that you will know it when it happens, but there's nothing you can do prior to that happening. And this relates to things like the halting problem. And it's this idea that I can determine in advance that there exists an algorithm that allows me to determine in advance whether or not there's another algorithm or program that will terminate. And it turns out that the algorithm will either go, yes, this terminates, no, this doesn't terminate, or it will execute forever. And when you apply it to itself, it can't determine the result. In other words, it's an undecidable result. See, it connects back to the earlier things. Now, what we've got here is kind of the challenge. We know that not all of this stuff can be known, and we see this play out with things like, I don't know, with naming. When naming things like tables, always future-proof. If you sell wine, calling a table wines will be confusing when expanding to beer. Beverages will be confusing when you sell ice. Products confusing when expanded services. So we recommend you call your table stuff or table one. Okay, that's the point. Whenever a developer says, I'm future-proofing this code, it's like, how can you future-proof this code? You don't know the future. You're just arbitrarily making your code more complex, or your name's woolly. You do have to make a commitment, but you have to recognize that commitment is contingent. And people get wrapped up in a whole load of things like roadmaps. I'm very critical of the roadmap metaphor, not because it's a bad metaphor, but because people clearly don't understand how roadmaps work. This is a kind of roadmap PowerPoint template. You know, having been critical of roadmaps and how people use them for products and architecture and so on. First year of the pandemic, I had a little more time on my hands, so I sat there and I kind of thought, okay, let's just Google. Let's find some roadmap templates. And lo and behold, there are loads of PowerPoint templates out there for this stuff. And they look, a lot of them look like this. They show you a pretty road. You fill in the gaps. This is great. The only problem is this is a roadmap. This is basically where I live. I live in Bristol. And as you can see, it's got more than one road. As I wrote recently on DevMio, the whole point of a roadmap is it shows you a network of roads, not just one. A real roadmap is filled with possibilities and choices. That's the point. Okay? Next time somebody shows you a roadmap that's only got one road, raise your hand. Say, where are the other roads? Why would you show me a roadmap that's only got one road? There's no point. You just say, keep going until you hit whatever. It's an itinerary. We're going to do this in 6 months, that in 12 months, that in 18 months. That's not a roadmap. That's just an itinerary. What you need is to show the branches in the road, the possibilities that you've acknowledged, and it highlights your awareness of uncertainty. But it also shows that you have some idea, but you're prepared to go with the flow. My favorite discovery during this period was this one, this particular one. I love this because it was obviously written in 2018. Here's your roadmap, fill it out with bits and pieces. Yeah, guess what? Nobody had for 2020. This is the major pandemic that upsets that upsets everybody, messes with your clients, messes with your work, life balance, and everything. That was not in people's project plans. That's the whole point. You cannot know the future before it happens, which also means, as an important side effect, that you cannot prioritize your requirements by business value. And let me be very clear, I'm not telling you that you shouldn't, I'm telling you that you can't. Because of our understanding of the laws of physics, you don't know the business value of a feature. You cannot therefore prioritize by it. Oh, you can prioritize by the business value estimate, but you need to tell people when they say, oh, well, let's prioritize by business value, remind them to use the word estimate, because it is an estimate. You don't know the business value of that, okay, until it's happened, until you have a way of evaluating. That point is in the future. And if somebody says, oh, yeah, you know what I mean, estimates are the same as actuals, then now you have a very different conversation, because estimates are not the same as actuals. The wisdom of Yoda tells us all of this. Impossible to see the future is. Okay, so on the home straight, a distributed system is knowable. I kind of promised we'd touch on this. And an observation from Martin Fowler a couple of years back, he found a nice little bug. Kevlin, you ought to know that United may have discovered a kink in the time-space continuum of the Atlantic. Sadly, they weren't able to take advantage to get me home earlier. The issue he's highlighting, apparently the time to destination when they were just past Greenland, which is not part of the US, and he was heading to the US, when they were just past Greenland, 2,500 kilometers to go, but apparently it's going to take them 0 time. Now, the distance between Heathrow and Newark Airport is just under 5,600 kilometers on the Great Circle route, this is not centimeters, this is light milliseconds. Already, by the way, there's an additional, we could actually split out an additional possibility here. If you have a server in New York and a server in London, and somebody says, we need these to be in sync, to no worse, they must not have any latency between these servers of worse than 10 milliseconds. That is impossible. Because if you can do that, there's a Nobel Prize waiting for you, okay? It's just not a thing, okay? So distribution is where, a distributed system is where effects like this take a hold. I co-authored this book a number of years ago, and we talked about distributed computing. And so a definition we've got here, a distributed system is a computing system in which a number of components cooperate by communicating over a network. That's not a bad definition, actually, looking back. The one that Leslie Lamport offered us is actually also quite good. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. Now, there is something that governs this. This is my publisher for 97 Things, O'Reilly. Fire in California, you can't read your ebook in Pennsylvania. Yeah, this is a good example of Lamport's observation. But I'm going to move from Lamport to Brewer, Eric Brewer. A thing called Brewer's theorem, which is actually better known as CAP theorem. It was originally a set of principles, then it was formulated as a conjecture, and then in 2002 it was actually proven as a theorem. Some of you may have heard of CAP theorem. If you haven't, here it is. CAP stands for consistency, availability, partition, tolerance. Consistency basically means that wherever you are in a distributed system, if I access a piece of data and 2 different points access the data, imagine it as, you and your friend, you're both looking at a social media network and you're looking at the latest post from somebody. Consistent basically says that you are going to see the same. You're going to receive the most recent update, and you're going to see the same thing. Okay, everybody has the same view of the data once it's updated and once they requested that data. Then you have the question of availability. Every request will receive a response, a non-error response, okay? And then you have partition tolerance. A network partition is when one network becomes 2, basically. A router fails, a computer goes down, whatever. The idea is that you've got a failure there. What CAP theorem says is, guess what? You can only ever guarantee 2 at most at any one time. You can have consistency with partition tolerance. In other words, you will always get the most recent update, or you will get an error mode. But the whole system keeps on running. Even when the router's down, Your bit of the system, as in your phone, will keep on running. It won't crash. But you're getting an error message saying, hey, guess what? This isn't working. Alternatively, we can go for the caching solution, availability. In other words, you're getting an answer, but it's out of date, and therefore somebody else might be getting a different answer. Or you can have both, but you don't get the partition tolerance. From the point of view of the Hitchhiker's Guide to the Galaxy, this is a kind of an observation that satisfies, or this is, CAP theorem satisfies this idea that we demand rigidly defined areas of doubt and uncertainty. CAP theorem is the Heisenberg uncertainty principle of the network. Back to Phil Carlton's observation, this is cache invalidation. This is the issue. But we also find that sometimes people don't quite get this right. You've probably seen this as well. I've seen this a number of times on different sites where there will be something that says, hey, there are 2 things here, and you see the list and there's 3 things. The correct answer is this. People sometimes say, oh, it's eventually consistent. It's like, no, this is called a programming bug. It is a feature of a distributed system that it may not be in a consistent state, but it is a bug for a client to contradict itself. Okay, if you're getting things from 2 different sources of data, one of those will be dominant. Normally you have 0 items, 1 items, 2 items. That's a more optimal path, and then you get the slower path with all the data items. That's fine. But if you show 5 things and you say there's 4, then there are 5 things. Okay, you don't justify it through bad programming. Okay, the final thing, and I recognize I'm a couple of minutes over time, but guess what? I have that one accounted for. I will show you in a minute. Technical debt is quantifiable as financial debt. The thing we've known since the late 1970s, and this is a 1980s quote from a quote from 1980 from Meyer Lehman, as an evolving program has continually changed, its complexity, reflecting deteriorating structure, increases unless work is done to maintain or reduce it. Notice he's using the term maintenance here in a way that is appropriate. We are talking about not maintenance as in bug fixing. He's sort of saying maintenance as in maintaining the quality. Whenever you make any modification to the code, no matter how good your intentions are, because of the nature of human focus, you are likely to miss something. Even when you are doing the cleanest, best code that you could possibly do, there is a chance there is something else that you overlooked. Okay. And you will only realize later, or somebody else will realize it. Now, people often talk about quantifying this in terms of technical debt, but this is kind of catching the wrong perspective. The real issue here that we actually suffer and experience is the problem of technical neglect. Debt is the measure of what happened, but why did we get there? We're not asking the question why. Neglect is the reason that it happened. We've got to get better at addressing that issue. Now, it is a wonderful metaphor. It was originally introduced by Ward Cunningham, and it allows us to reason about some of the issues. And as Martin Fowler says, like a financial debt, the technical debt incurs interest payments, which come in the form of extra effort, maintenance effort. The point is, every single software development project needs to account for maintenance cost. And that's not because you're writing bad code. You could be writing the best code ever, but to maintain the conceptual integrity, you need to have extra work. Just as you cook the best meal ever and you are working as cleanly as possible in the kitchen, you still have to do work to keep the kitchen clean. It's not because you're doing a bad job, it's just because you are doing work. It's a function of physics. The fact that you are doing work means that if you wanted everything to be as tidy as it was before, this is second law of thermodynamics, you need to put work in. Okay, additional work, maintenance work. But Martin talks about you can't go around telling people about physics. People relate to money. So financial debt is a really interesting metaphor. And it's the idea of saying, okay, if you don't repay this, the interest goes up over time. But let's be really clear. Let's go back to that statement. It's a metaphor. Okay. And I often find myself doing this. I found myself cautioning against the category error of treating the technical debt metaphor literally and numerically. In other words, converting code quality into a currency value on a dashboard. You can't do that. The laws of physics tell you can't do that. It's a metaphor. You're not supposed to do that. It doesn't matter what number comes up. That number is pure fiction. Or if I'm being a little more brutal, it's bad science. And sometimes people say, oh yeah, but we've estimated how much it would cost us to repay the technical debt in terms of hours of work. Well, first of all, that's an estimate. It turns out that my bank balance and so on are not estimates, they're actuals. But the second thing is, that's a misunderstanding. Debt is not the cost of repaying the debt. The whole point of the debt metaphor is it's the cost of owning it over time. This is the message. It's not simply a measure of the specific work needed. It's the additional time and effort, and it's all the past, present, and future work, and we know that you can't predict the future, that comes from having the debt in the first place. So I've got a bonus for you. I've got a bonus 0. My bonus here is finishing on time. That is sometimes impossible for me. So apologies for stealing an extra 5 minutes of your time. But it is this clear and simple reminder: reality cannot be ignored except at a price. We work in worlds of abstraction. It sometimes feels like we can create anything, but we are still bound by this universe, sometimes constrained by mathematical possibilities, but even more brutally by physical limitations. So I will be heading over to Gathertown now to answer questions. And also, if you want to ask questions of me on social media, more than happy to connect. But in the meantime, thank you very much.